an analysis of the Lab 7A, which you've already turned in and I've already scored. So here's some feedback based on what I saw, some things that may be helpful. So one thing that I saw was that many people, enough to make me say this, did not record their voltage or current. They just recorded the power out. That is not okay. You must, absolutely must, when you do a lab, you must show your observations. That's non-negotiable because you don't have a meter that measures power out. The way you got power out is by measuring voltage and current, so you must show that. Alternatively, if you didn't do 3 trials of voltage and 3 trials of current, then you may have done runs like this where you may have had 15 different distances and you did 1 trial of each. So this is possible also, but you absolutely have to show the values that you get. So, so either way, either like this or like that, doesn't matter to me, but you must show your observations. So that's the first thing that you need to make sure you do. Second thing, so here's, you also want to record all your givens. Most of you did do this. That was great. So you showed the power of the light source. Some of you calculated the intensity, but this piece we have to talk about. And we need to talk about the difference between power in, the power of the light source, and the power out. So we'll get to that in a moment. We're going to make our graph because that is, of course, the best way to do it. So I'm going to graph this 2 different ways because in each class I kind of did 2 different things. So the first graph here, that was for regular physics, we did distance versus power out. So you'll notice that this is a inverse graph. So we want to know, well, how inverse is it? Is it direct or not direct? Is it to the power of 1, power of 2? So to add our trend line, we're going to go in here and notice how the linear relationship does not fit at all. So we're going to pick a power fit. Some of you still insist on using exponential. Those of you who have been paying attention, I have told you countless times, we never, ever, ever use exponential. You don't even really know what that means. So please don't use it. Exponential does not mean that x has an exponent. It means that x is the exponent. This is not anything that we ever do in this class. So, we've got less than a handful of labs left. Please stop picking this. Okay, I don't know how much more emphatic I can get. You only have 3 choices: linear, polynomial, and power. Power is always a good default if it's curved. Anyway, to get the equation, we're going to do this, and you'll notice that this is to the power of -2, which means it's an inverse square relationship with distance. Okay, so that's one graph. So I'm going to make another graph here, and we're going to do, for the other class, I had to do intensity. So I'm going to just alter this so that instead of using distance, we used the intensity, which I didn't calculate, so I can't do it yet. Let me calculate that real quick. I didn't do it for this data table. So the intensity from the light source is going to be the power of the light source divided by the surface area of a sphere. Let me show you you can see what I'm typing up here. So the power of the light source divided by the surface area of a sphere, which is 4 pi times the distance squared. And that'll give me the intensity of the light source at the location of the solar panel. So now I'm going to fix this by going into select data, and instead of distance, I'm going to use intensity. And then this should be power out. Just checking that, and then I can say okay. So this should be a linear fit. You can see it's not perfect. I can actually put on a linear fit. Right now it's still a power fit. This is to the power of 1, which means it's linear, but let's just fix this to be linear. We can also set the y-intercept to 0. I also want to show you, you see how this only has 1 sig fig? I can show you how to fix that. If you click on the box for the equation of the trend line and click on here, you can change this to number, and you can change the number of decimal places. So that should add, that's only 4. Let's say I want 7, which is kind of goofy, but it'll give me 7 decimal places if that's what I want. Then that's what it'll give me. So you can add decimal places. So these are this is the graph for honors physics. I have to fix this to be intensity of the light source. Intensity of the light source at the solar panel. And it'll be in watts per meters squared. Okay, let's spell this correctly. That's that. I want to show you the theoretical derivation. It's exactly like what we've been doing for the problem solving. So most of you had the light source up here and the light was shining down, and then you had your solar panel here. Some of you had it set up where the solar panel was like against the wall and here's the light source, but it's the same thing, just tilted on its side. So I'm not going to do it twice. But you can see that the light here, as it shines down, right, the closer you are, the more these rays are going to actually hit the light source, hit the solar panel. So that should hopefully make some sense. The power of the light source, it was different for everybody. You know that though. And you also know the distance here. This distance was your independent variable. This is what you were changing, no matter what you were graphing. And that this was part of the intensity equation. So this distance changed the intensity received by the solar panel. Okay, you also knew the length, or you measured the length and the width, so you could get the surface area of the solar panel. One mistake some people made was they, if this was like, I don't know, 5 by 12, some of you did, this was 60 centimeters squared, and this said this was 0.6 meters squared. That is incorrect. It's 0.006 meters squared. And you should have checked that by converting the length and the width to centimeters and then multiplying. So this is not correct. That's something to please keep in mind. You convert each one individually and then multiply them. Okay, so now this was connected to your light bulb, to your LED, and you measured the voltage and the current. You multiplied those together to get the power out. So this was your dependent variable. Okay, so that's that was the setup. So then how do we interpret our graph, or how do we predict what our graph should be? So I'm gonna start with the different equations. We have a bunch of them. So we have this power out equals V times I. We also have the efficiency equation, which is P out over P in times 100. I'm going to substitute this in for, actually, I'm not going to. Okay, so we know that this we can get pretty easily. I'm going to rearrange this so it's P out equals E divided by 100 times P in. So I'm just rearranging. Okay. So the power received by the solar panel is related to the intensity, right? So the power into the solar panel is the intensity times the surface area of the solar panel. So this here goes in there, and the solar panel surface area goes in there. But I'm not going to put numbers right now. I just want to do substitution. So we'll have efficiency divided by 100, and instead of power in, I'm going to substitute that. So intensity of the solar panel times the surface area of the solar panel is power out. So now I've got my Y here and intensity, which is on the X. Now, for some of you, right, you need D on the X. So let's substitute in the intensity equation, right? So the intensity equation, right, is going to be the power of the light source divided by 4 pi d r squared. This is on the Y, and this is on the X. So what's the relationships now? So this here to here, that's linear. This to this is inverse square. So you can see that from this derivation. And this is not something to memorize, this is something to understand. So before we finish this up, I really want to distinguish between power out, power in, and power of the light source. This is what the solar panel uses the energy to do. It's the energy used by the load. That's another way to say it, okay? Or the rate at which energy is used by the load. That's a little bit better. Okay. Power in is the rate at which the solar panel can be absorbed or can absorb energy. And this is limited by the efficiency of the panel and the surface area of the panel. Doesn't that make sense? And the intensity it's receiving. Okay, so there's three things that affect the power in, and that's reflected in these equations. You've got the power of the light source, the surface area, right? That's all the intensity. You've got this and you've got that. So those are the three things that influence the power that the solar panel can absorb. And the power of the light source is the rate at which the light source produces energy. Okay, so these are not equal to each other. They are different things. You can't, if you just write power, you're going to be very, very confused, and you're going to mix them together. So I really spend a lot of focus on making sure I distinguish between those three things, and I understand when to use each one, because you're going to use different equations or the same equation to do different things. And that's really about understanding why you're doing what you're doing. So now back to our graphs. When you go to, now that we've derived this equation here, let's use it to interpret our graph. So I'm going to rewrite that here. Power out equals efficiency over 100 times intensity times the surface area of the solar panel. If on our graph we had an equation, the equation of our line was y equals 0.00057116x, and we did power out equals 0.00057116, and instead of x, it's going to be intensity. So this was the graph we did on Excel. So what do these things mean? Well, power out and power out are the same. Intensity and intensity are the same, and the equals are the same. What's left? Well, we have efficiency and the surface area of the solar panel. That product must be the slope. So efficiency divided by 100 times the surface area of the solar panel is 0.00057116. So if I know what the surface area is, where is it? On my Excel, I'm peeking here. The surface area is 0.00754 minus, right? If my surface area of the solar panel is 0.00754, and I can plug that in there, and I can find my experimental efficiency. So before I showed you on the data table, you could figure it out for individual points, but it's always more sophisticated and better results if you use the equation of the trend line and interpret that. If you but there's more than one way to take a look at this. So let's see. So 0.005716 divided by 0.00754, and that leaves me 0.758, which means my efficiency is 75.8%, which is not very good. Which doesn't match my 10.2. So something maybe I used a different values for this. Let's see. Do I have it on here? I don't think I have it on this particular one. Okay, so power received. Yeah, so that's how you would interpret your graph. If you are in the other class and you did, let's do this again, but we'll do it for the distance. So let's copy this. So instead of intensity, your theoretical derivation had power of the light source over 4 pi distance squared. So we've got here only this is on the graph, right? Yours looked like this. Okay, this was your theory, and your equation was y equals 0.0105 x to the negative 2. I'm just rounding my exponent. So this here, my mathematical model would be power out equals 0.0105, and this would be 1 over d squared. So when I go to interpret this now, I want all of this stuff is going to be equal to that, because power out and distance squared are the only things in my mathematical model. So now I can take out E over 100 times P of the light source over 4 pi times surface area of the solar panel. All of that is equal to 0.0105. Now plug in what you have. You could do it a bunch of ways. You can solve it for any of these things. You could solve it for your efficiency, since that's known. You could solve it for the light source power, because you know that. You could solve it for your surface area. You could do that. So let's solve it for the power of the light source. So if I know that this is 10.2, just to do it a little differently, and this was 0.00754 equals 0.0105. Okay, so 10.2 divided by 100 divided by 4 pi times 0.00754. So this would be power of light source times 6.12 times 10 to the negative 5 equals 0.0105. So divide, 0.0105 divided by that previous answer gives me 171.6 watts. Now, if you look back at my data table, I used a 200. So this is my experimental light source power. My actual power of the light source was 200 watts. I can do percent error now between these two things. So if I do percent error between those, I know it was actually 200. Well, that gives me a 14% error. That's not bad. That's pretty reasonable. So that's another way you can evaluate your results. There are multiple. You don't have to do every single possible way, but you do need to do at least something where you're evaluating your results, and you want to really use your equation of your trend line and your mathematical model and your theoretical derivation to really work on the overall trend and see how how this worked out. Here's a lab report from a student last year that while there's still a couple of mistakes, it's really nearly perfect. So I thought I'd just use it as an example. So take a look at the methods and materials, look at how thorough it is. I don't, it's not perfect, right? They still are listing equipment, which I don't ever want you to do. That kind of drives me crazy. So that stuff I would want you to take out. But they talk about the ammeter, how they set it up, how they linked it together, right? They have a diagram here that they reference, and everything is labeled. They also put in analysis, which is not needed, so I would cross that out. They also put in, but they did talk about how many trials they did. She didn't mention, reducing, they did that 15 data points in order to reduce experimental uncertainty. So there's little things here and there that could be fixed, right? This was a problem-solving setup. It's really not complete, right? So, but they did show that she did show this diagram of the circuit. She showed her prediction here, and we'll get to the problem-solving setup in full later. Here's all the data. She has a title for her data table, which is always good. And then she did 15 trials. I know some of you did 3 trials each of 5 data points. She had 15 data points, and she called it radius. I know that you don't have to do that, but she's kind of making sure she remembers what that distance is. And then she got the power output, and she figured out intensity, which you didn't have to do in regular physics, but you needed for honors physics. So here's a sample calculation. Again, this is not anything that I don't love this format. I'd much rather have that be as a math problem, equation, numbers plugged in, answer with units. And she forgot to do intensity. So showed an example of her capstone. By the way, I think that a better way to do the intent to find these values, to record them, is to put it into a data table, have a column for voltage and for current, and use the keep, as opposed to use the keep sample instead of continuous mode. That's how I would choose to do it, because it makes a data table and all you have to do is copy and paste it. But this is fine, this works. Then she made her graph, and notice she changed the number of digits here. That's important. I showed you how to do that when I showed you the Excel just earlier. For those of you in regular physics, instead of intensity, you would graph distance, and you should get a nice squared relationship, as I showed you. The graph interpretation, here's the equation of the trend line, here's the mathematical model, and the R squared. So then this here is her theoretical derivation, and she walks through the theoretical derivation, how did she know the slope was area times efficiency, and what area is she referring to? So she's explaining that and showing it very, very clearly. Percent error, she found 2 different ways. She found using her theoretical value of slope that she figured out up here, and then she compared that to her actual slope, or her experimental slope. So she got under 20%. And then she also used percent difference between her value and the class value, which a lot of you did, but because most people made errors in their graph, making their graph, the class average was not useful, it was awfully wacky. Sources of experimental error can be the ambient light, which many of you mentioned, and she does a great job of explaining it. Also, measuring the distance between the solar panel and the light source was hard, because where exactly do you measure the beginning of the light source? It's round, it's hard to get that straight, it's hard to measure inside of the lid. For those of you using the green halogen light sources, those are really hard to figure out where the light source was from the outside. So there are a lot of reasons why measuring distance was difficult. Also, the angle of the solar panel was not necessarily constant or easy to arrange. So those are all issues that you could have mentioned. Some of you mentioned the variation of the voltage and the current, but we get such precision with those meters that that's like a very minor thing compared to the other bigger things that I just mentioned. So that's that. So then there's the CER. So your CERs, the formats were almost uniformly perfect. However, because either your claim was wrong or your evidence was wrong, it was really hard for you to earn advanced or even proficient, some of you. So we just need to clean that up. Don't change the format. A lot of your reasoning was really well done. I'm very pleased with your growth in that area, but you got to get your claim right. So you have to be able to know what the theory says it should be and look at and choose the right trend line, or you're going to have a hard time with that. So last piece is look at the comments. She made 8. You know my minimum is 6. Look at how prolific they are, right? And how thoroughly she explained it. If you want advanced on the commentary on annotations, that's what you have to do. Some of you are asking me great questions, but then forgetting that you also have to explain what did you fix and why did you fix it. So don't forget, you have to do the developing and proficient levels before you can earn advanced. So I hope this was helpful. I know this was rather long, but I think there's probably a lot of really good things you can get out of it. At least I hope so.